In this video we're going to look at induced EMF, i.e. creating a voltage by rotating a coil of wire or several coils of wire within a magnetic field. So generator, the idea of a generator dynamo type idea. Okay, let's get cracking. Okay, so there's the formula that we've got from our formula sheet, the ways of calculating our induced EMF. We'll take each one in turn, just so we're happy with the way that things calculate. Okay, so if we take this formula first, so if we know the number of turns of our conductor, we know the change in the magnetic field over a change in time, then we can then work out what the induced EMF, what the voltage is going to be. So let's look at it with an example. So here we have a question, 50 milliwebers of flux, 2,500 turns on a coil, and we're going to reverse the rotation of our coil in over a space of 20 milliseconds, so we can find out what EMF is induced. And in this case we get minus 6.25 times 10 to the 3 volts, so minus 6.25 kilovolts. So quite a substantial generation there. Okay, that's as straightforward as they are. So if we take the next one, BLV, flux density, length of the conductor, and the velocity of the conductor. Okay, so a 50 centimeter conductor moved 30 centimeters per second, right angles, flux density 5 Tesla. So let's work out what the EMF is. So if we pop all of that into our calculator, then we get an answer of 750 millivolts. Okay, quite straightforward. Things we need to watch out for is that all of our units are obviously in meters, and then obviously the velocity there that needs to be in seconds. So if you get anything else in seconds, then you've got to, if it's in 30 centimeters per minute or per hour, then you need to obviously convert that as well. Okay, just one extra little note within the video. So we're saying that we're moving at right angles, so we need to take into account if we're not at right angles. So I just want to make you aware of that. So this V part of the equation, we need to take into account the angle. So the V becomes V sine and whatever the angle is. Let's just see that in action. So if we then say that we're going to move it rather than 90 degrees, we'll move it 60 degrees, so we're not getting our full induced EMF, maximum induced EMF, because we get maximum at 90 degrees. Then we pop all of that into our calculator, then I think we should get 650 millivolts as our induced EMF. I'll just double check that. Yep, okay, so that's all there is to that. So okay, let's have a look at another equation. But before we look at that equation, we need to talk about inductors. So an inductor is basically a coil of wire, so that's what we show. Our symbol for it is just a coil of wire. The unit of inductance is the Henry, and it's quite useful in lots of circuits, so lots of filtering circuits and receiving circuits, to use an inductor because of the properties that it creates within our circuit. The coil of wire that we are using to induce an EMF can be classed as an inductor. So we can calculate the value of inductance if we know the number of turns, the flux, magnetic flux, and the current. So let's have an example. So we could have a question looking a bit like this. Or we could already know the value of inductance and get us to calculate what the flux is, and then I suppose we could then go on to calculate flux density if we knew the area of the magnetic circuit. So we end up with something like that. It gives us 1.92 henries. So we can now use this formula here where we've got the back to our EMF, working out the voltage that's going to be induced, so it's going to be generated. So if we know the value of inductance, so we know the change in current, and when over a change in time, we can calculate the voltage. Okay, I'll just pop that down, then we'll have an example question. So if we take something like this, then we can work out what the voltage is going to be. So minus L over di by dt. So we've got minus 183 millihenries times by the change in current is 2 amps over 5 seconds. So I made that 73 millivolts. Okay. Happy days. I think that's us covered all of the induced EMF voltage formulas. I'll just check. So one last thing with we'll finish off with this set of videos is the same as we could with our lots of other components. We can work out what energy is produced within the inductor itself. So energy results the answer is in joules. So L is our inductor. I is our current. Make sure you remember that is squared. Okay, and that's about it really. It's quite a simple formula, nice and easy to apply. So if we take a question like that, 512 millihenry inductor, 300 milliamps, what's the energy stored in the inductor? Just plug the numbers in. Plug all that in, and then we get 23.04 millijoules. Okay, I think that wraps this video up. Lots in it, I know, but a lot of them different equations for calculating our EMF. Okay, keep practicing and keep with it.